So we talked previously about decision regions. We talked about how we could formulate an efficient receiver which calculated the coefficients in signal space of the received signal and found whether in which region it fell in as an efficient decision part of the receiver structure. And now the next question is, how do we move forward and calculate the error probability for these regions? Well, clearly minimal distance is going to be an important concept in order for us to do this performance analysis. Remember, we defined the minimal distance as taking all different pairs of symbols and finding the pairs which were closest. It may be unique, or there may be several pairs that are all at this distance, but there's some distance which is the smallest distance between any two symbols. Call this the minimal distance, and intuitively we know the closer these signals are, the more errors they're going to be. And this is going to be the key to us finding a way of evaluating the performance of M-ary signaling. So pairwise examination of symbols is going to be important. So now we'll go into the performance analysis and try to come up with an expression for the probability of error for each one of these modulation formats that we've looked at in the M-ary case. So analyzing performance. And the idea is that we would exploit our results from the binary case and use some sort of geometric interpretation. So now we know what the receiver is doing. It's looking at regions and using that to help us understand how to do the performance analysis. So we're going to start from the binary case. What can we learn from this? Since we know that this minimal distance is defined by pairs of symbols, well, pairs of symbols sounds like the binary case. And so it gives us a little intuition what's going on. So let's say that we have two symbols. In this case, we assume that they're right on the axis with one of the basis vectors, which was the case in the binary we looked at, which was a one-dimensional space. But it's really a bit arbitrary. What matters is, say that they're in two-dimensional space, and that their region is not just on one-dimensional line larger than a threshold, smaller than a threshold, but it's two-dimensional space. Here are 2 points in that region. And we know that what we're going to do is find a perpendicular bisector between these 2 points, the midpoint between them, divide the plane into 2 regions. And if it's in the blue region to the right, we choose symbol 2. If it's in the red region to the left, we choose symbol 1. And again, I have this lying along a basis vector, but it really doesn't matter. And I'm showing two-dimensional space because it's just easiest for us to visualize, but really it could be n-dimensional space. The idea is I have a pair of symbols. And when do I make an error? So let's think back with the binary case. When is it I make an error? Well, suppose I have an arbitrary received vector somewhere in the two-dimensional plane that I'm examining now. Now, if we look at the example here, well, this R that I traced is clearly in the blue region. It's on the half plane where S2 is found. And so I'm going to choose S2. There's not going to be an error. So why is there not going to be an error? Well, it's because if I do a projection of that received vector and I find out what was the noise contribution, well, the noise contribution here would be the projection of this along this line connecting the two symbols that I'm deciding between. And here I'm calling it, say it's lying along the basis vector, just for convenience. But essentially there's going to be a noise component to this blue vector, which I've written in red, which sort of offset the black vector, which should have been the S2 if there was no noise. So I didn't get S2 with no noise because there was some noise that was pushing it. Now the noise happened to push it way up high, but the way up high has no influence. The only thing that influences this is the movement the noise forced along the line connecting S1 and S2. So we call that the projection of the noise onto that line connecting the two. And so what happens is if the R had gone in the red region, that this projection of the noise would have been bigger, and the projection of the noise along the line between the two would have been large enough to cause an error. So when is it large enough to cause an error? Well, when this noise component in this along the vector connecting the two symbols that I'm interested in, when that component of the noise is bigger than the separation of those two symbols. So we can say that this noise element, this projection along that line, is greater than 1/2 of the separation of the two symbols. So that would be the dividing line. If the projection of the noise along this line that connects S1 and S2, if it's larger than that half the minimal distance, half this distance is separation between the two, then I'm going to have an error. So now we can see we could take a binary case, which was really a one-dimensional space case, and really it's very generalizable to an arbitrary space. And as when it occurs that the noise element is greater than half of the separation between the two symbols, that's when we have an error. Okay, so I'm going to use this to try and do some analysis now of the M-ary case, when there's not just two symbols, there's a whole collection of symbols. So to do that, I'm going to use what we call the union bound approach. And so it's a bound that takes the binary case formulation and it stresses the contributions from the nearest neighbors. And in the approximation, it actually neglects contributions from more distant neighbors. So intuitively, the noise contribution doesn't have to be that big to push over to the nearest neighbor, but the noise contribution would have to be huge to push us over to a neighbor that's far away. So intuitively, we think the nearest neighbors is the most important part, and the union bound gives us a way to quantify this intuition about the nearest neighbors being more important. So the union bound. Let's take an example again, just for visualization to understand what's happening in the union bound. I'm going to take a simple case of QPSK. Then from QPSK, I'm just going to say, and we generalize it to the M-ary case. But QPSK, very simple intuition. There's 4 points, there's 4 regions, there's 4 quadrants in the two-dimensional plane. So very, very simple. So if we look here, here are my 4 points in QPSK space, S1, S2, S3, S4. They're located at 45 degrees. And essentially, there's 4 different decision regions. If I fall in quadrant 1, in blue here, I'm going to choose symbol 1. If I fall in quadrant 4 down here, I'm going to choose symbol 4. Very straightforward. So when do I make an error for symbol 1? Well, I make an error for symbol 1 when I don't fall in the blue region. I fall in the complement of the blue region. I fall somewhere in one of these other 3 regions. So I can imagine the union of these 3 these 3 other regions as representing where an error happens. So the probability of error, the probability of making an error when S1 was sent, so here it is, conditioned on S1 sent, is the probability that R falls in this union of these 3 decision regions for S2, S3, S4. So if it falls anywhere there, I'm going to make an error. Okay, so what I'm able to do is analysis pair by pair. So I'm going to take this S1 and I'm going to start examining what's the probability that I'm going to mistake S2 instead of S1. What's the probability I'm going to mistake S4 instead of S1, S3 instead of S1? And then from those individual contributions, I'm trying to intuit something about the probability of it falling anywhere in this union of these spaces. So let's take the first case, S1 versus S2. When am I going to make an error? So that would be the probability that I would mistake S2 for S1 would be the probability that S is chosen when S1 is sent, of course, and it's the probability that it is not in, received signal is not in this half plane, since now we're just looking at these 2, as if only these 2 symbols were present, as if S1 and S2 are the only ones that exist. And now if I look at S1 and S4, it would be, again, the probability I fall in this upper plane versus the lower plane. And, you know, these 4 points that I chose, they happen to be these 2, S1 and S2, and S1 and S4 are equidistant. They're the same distance apart from one another. And so these two probabilities are going to be the same because the distance between S1 and S2, the distance between S1 and S4 is the same. So they're going to have the same probability. Now, if I look at S1 and S3, well, these are a bit farther apart, right? They're not as close as S1 and S2 are. They're across the diagonal here. But still, I could calculate what the probability is by calculating this distance between S1 and S3 and using that to determine what the probability was that I would make a mistake from S3 to S1. Now, what the union bound says is that the real probability of error is the probability of falling into this one little wedge, or this quadrant. But that is going to be upper bounded by doing a sum of all these other pairwise probabilities. So for sure, the probability of falling in each one of these three regions that I've determined here, these three probabilities, that's going to be a bigger probability than the true probability, which is falling into this one quadrant. Okay, so just so I can be clear, I'm going to go back. Here is one region, which is the right half plane, another region, which is the top half plane, and then there's this 45-degree angle half plane. And so that's what I've sort of traced here. The left half plane in these blue dotted lines, the lower half plane in the red dotted lines, and then in the blue slanting lines at 45-degree angles. So if I look at the sum of these three probabilities, they represent the sum of calculating the probability over all these different regions. Clearly, it's a bound. You know, it's going to be smaller than this. So the probability of falling in this quadrant is smaller than the probability of falling into all these different regions. And now let's look at what's really going on in this sum. Well, in this sum, I'm counting this quadrant 3 times. I'm counting these sort of half quadrants 2 times. And then in the main, these green areas here, I'm just counting these things once. Okay, so when I'm doing this summation, when I'm getting this bound, there's some things that I'm counting, really overcounting. Like I'm counting this region in each one of these 3 terms. I'm calculating the probability of falling in this lower quadrant. So, you know, I'm really overestimating it by 3. But we have this intuition about the, well, first of all, what's interesting about QPSK is it's a simple enough problem that I can actually find an exact solution for it. And I wrote here the equation for the exact solution for this QPSK problem. So I won't go into it. It's a little bit trick. But you can use a trick and you can calculate this is the true probability of error. Now, what I look at this, and I see there's 2 terms, and I look at the first term, which is in the 2EB over N0, and a second term, which has got the square root of EB over N0. And this first term is really dominating the behavior. And this is dominating, and it's, if you looked at it numerically, it's like if I was integrating to find the probability, taking this Q function and integrating it over the whole space. Most of the action is happening in this area here, which is in dark green. Most of the action, most of the contribution to this calculation. So although it's a bound, I can use it as an approximation. And we call this the approximation coming from the union bound. So although I'm actually summing up all of these probabilities by using this approach, taking it 2 by 2, every 2 symbols, in actuality, it's just the contributions that come from the nearest neighbor that are having an effect. So this approximation from the union bound in the case of QPSK would be to throw off the second term and just keep the first term. And the first term is essentially the calculation between this nearest neighbors, so between S1 and S4. That would be one of these Q, the square root of 2EB over N0, because the distance between these is 2EB, the square root of 2EB, and the difference between S1 and S2. That's why we have the factor 2 out in front. So what's inside this Q function, is the distance between S1 and S2, which is the same as the distance between S4. And the multiplicative factor in front is how many times that distance occurs, and it occurs twice here. So the extrapolation to the M-area case is that what we should do is take this minimal distance, this d min that we've described earlier, put that inside of the Q function, and then the Q function, we should have a multiplicative factor, and for QPSK it was 2, but actually what we're doing is 2 times k divided by m would be the correct multiplicative factor that takes into account the number of pairs of symbols that are separated by the minimal distance. So in the book, they do not give you this derivation of the union bound. However, you will see equations for MPSK and square QAM, and they will match this union bound. So they don't give you the derivations in the book, but I thought it was interesting to show you how signal space is the key to finding performance even for higher order modulation formats. And this could be a good approximation even for very arbitrary geometries, which aren't quite as simple as the QPSK I showed you, or maybe even some other simple ones.